Thanks everybody for joining the Zoom call. Today we'll be talking about how to serve Bert models in production, particularly in the context of the PyTorch inference server called TorchServe. So today's agenda will be we'll be talking about a little about the use cases for machine learning that we've seen at Walmart. We'll review some deep learning concepts. There'll be a hands-on session after that, where we have a Collab notebook out and we'll do some hands-on work with there. There will also be another hands-on session after that. We'll also talk about a little optimizing the model for production, so post-training steps, pruning, model distillations, that kind of stuff. We'll do a hands-on on that as well. After a short break, we'll do another hands-on on how to deploy the model. And at the end, you'll see a live session, and you should be able to run live inference on a Torch server. So once again, my name is Adway, and we have Nidhin on the call. We're both machine learning and software engineers at Walmart. We work on the search team. So a lot of the problems we work with are search ranking, search relevance, and personalization kind of problems. So the use cases that we see at Walmart Search for machine learning, some of them are spell check, type ahead, microservices, guided navigation, item and SKU understanding. So item and SKU understanding is usually an async task. We have models running 24/7 pretty much that understand how better to decipher SKUs and SKU attributes. And then on the runtime side, we have query understanding models, which are live and at runtime when the user inputs a search query, given a product, gender, attributes, age, size. These models try and understand these attributes semantically much better, and then match them on the SKU side to better yield relevant search results for the search engine. Personalized ranking is another use case that we see at Walmart Search. So here you see the use cases in action. On the left, you can see type ahead. Given a query, we're giving the customer some type ahead suggestions on what or to better narrow down on what the intent of the customer is going to be. On the right, you see guided navigation builds. These have been populated given our deep learning models. So customers usually that start off with a query such as milk, through the customer journey, end up at a certain other product and a SKU. This could be almond milk, this could be lactose-free milk or chocolate milk. And then we extract these attributes from the end destination at where the customer ended up. And then that's how the model learns for future users, where a query is very broad and how to narrow down the intent of the customer. So again, another example. So this is from our product type classification models. So given a query of Nike men's shoes, we extract the brand as Nike, gender attributes are men, and our product type classifiers ascribe a confidence score to each of the product types. Athletic shoes here has 99%. Casual and dress shoes could be another product type. Here it's ascribed a confidence score of 55%. On the SKU side, it maps it onto whatever the relevant SKUs it deems appropriate. So here you can see another SKU, Nike black and white, shoe size and 7.5 as a relevant search result. So what are the requirements, and what was the motivation behind our TorchServe discovery to serve models in production? So currently, most of our models are in TensorFlow and Onyx backends, and they are served in a Java native environment. So these are Spring Boot services usually, and they load the models in memory, and then they're run in a Kubernetes cloud-based environment. We want to search larger models like Bert, and this is where TorchServe comes in. TorchServe also has a lot of other advantages, which we will cover on later in the presentation. We work with strict SLAs in production. We have strict requirements as to what latency should be and what the throughput requirements are going to be. Since most of our microservices operate at an SLA of under 40 milliseconds, we see that TorchServe on a GPU-based environment, since TorchServe provides a lot of support for GPU and CUDA, optimizations seems to yield really good results. So this will be the repo that we will be using during the hands-on session. I'll cover this later on. So for the hands-on session, we have a data set that was published by UC Berkeley, and it's got products from Amazon. So this is what the SKUs look like. The SKUs have information on the brands, the item IDs, item names, product types. This is what the data set looks like, and we'll be using this to run live inference on a Torch server. At the end of the hands-on session, you should be able to make a simple REST call to the Torch server, and the product type classifier that is hosted on the Torch server should yield product types with confidence scores as shown here. So given your query of verbal T, here it shows T as it deems T to be the most appropriate product type with a 72% confidence score. So let's review some deep learning concepts before we get into the hands-on session. So where were text-based models for these kind of use cases before BERT and transformer models came by? So we had word embedding models, and we had Word2X, we had Glove, we had Elmo, and these kind of models. The problem with most of these models was that they were not, most of them were not bidirectional to start with. Some LSTMs, long short-term memory models, were bidirectional, but they were not deeply bidirectional. So I'll give an example. So let's say let's take two sequences of two separate sequences of words, riverbank and bank deposit. Both of them have the word bank common, but if the model goes left to right or right to left, the context of the word is very different, or of the word bank is very different in both the sequences of the word, in both the sequences. So this is an example where these models fell short since they were not deeply bidirectional. They would lose the context of the word. Even shallow bidirectional models such as bidirectional LSTMs, since they went left to right, learned the context left to right and the right to left separately, and then ended up concatenating them, the deep meaning, the deep semantic meaning of the word was lost. This is when transform models came by to alleviate some of these issues. On the left, you can see a typical LSTM model and how it works. So some use cases where transform models came by and went on to help us give BERT. So some use cases where these models were used: machine translation, question answering, sentiment analysis. As I mentioned in the previous slide, we did not have contextualized embeddings. That's something BERT solved for us. This was the first truly deep bidirectional model. In a transform model, if you stack up all the encoding layers, you get a BERT model. Since this was a general language model that was trained on tasks such as masked word prediction and next sentence prediction, and in a semi-supervised manner, it could be trained on a much larger corpus of words. The tokenizer also solved for out of vocabulary words. Something that really helps. Let's say you have a spelling mistake or something. In that case, you don't have a word in the vocabulary, and BERT alleviates that issue for you again. So again, we stack the transformers encoding layers, and you get a BERT model. And it's on the left. You can see a BERT model in action. So BERT has different architectures. We see, given the BERT recipe, we have multiple versions of the model. If we tune the number of attention heads and the hidden size of the models. So here we have a small table with BERT tiny, mini, small, and medium. These are smaller than BERT large and BERT base models. They've been there. We see the last two columns show the glue scores for two of the relevant tasks that we deemed to our use case. So SST is the Stanford sentiment tree bank. This is a data set, and then QQP is a Quora question pairs. And you can see that you can see how the models perform on these glue tasks, and how they progress once we go from lower layers of complexity to higher. So by LSTMs and Bert, we ran some predictions for the query betting for twin Excel matrices. You can see the confidence scores. We got a pretty good F1 score improvement. F1 is a metric that combines the relevance and the recall of a search engine. And you can see the improvement went from 0.75 to 0.91. So that was a pretty big improvement. Again, to showcase the motivation behind Bert and how much Bert helped when it came by. I'll be handing over the talk now to my colleague Nidhin. He's going to run through a hands-on session. Nidhin, take it over.
Thanks, everyone. Thanks, Avi. As you guys know, we have this Slack channel serving PyTorch models in production, where, again, we have shared the repo and slides, but I also shared it on Zoom chat if you have it. But again, the link is just bit.ly/PyTorch workshop 2021. I'll just share it again in the Zoom chat. So this is the setup portion. So, if you face issues while, setting this up on your end, and especially if you're interested in running the notebooks together, please do raise any issues in the Zoom chat. So this is our repo. If you scroll down a little bit, so we have several notebooks, but let's just click this link here, open in Collab. So this is just a starter notebook that we'll have. So if you click it, the content of the notebook is not that important. It's just like some setup pieces. So just click runtime, run all. And for our workshop, since we won't actually be doing training, we'll mainly be focusing on inference. So you don't need to have like a GPU runtime or such. And the default CPU runtime is sufficient. So just click runtime, run all. And the steps might take about like 3 minutes or so. Basically, like since we have several notebooks that we want to go over, basically inside the Collab runtime, we're just cloning the repo, cloning the data set that we talked about, cloning a model that we trained on the specific data set, installing the requirements that we need, and then basically installing like a VS Code session so we can basically interact with the Collab environment a little bit more interactively. So this again may take 3 minutes. If you face issues or, please do share in the Zoom chat. Also, feel free to ask any questions about the earlier section too. But basically, just to summarize, in production, we started with a bio-LSTM model, and we were interested in Bert. And as you saw from the F1 score, that's actually our actual production F1 score on our eval data set. So that was a huge bump, and definitely we were interested in pushing this into production. And okay, so this again might take 2 or 3 minutes or so. So if you want to follow along, feel free to run this. We also have in the repo like the already pre-executed notebooks. So if you just want to read it also, that's fine too. So basically, we are using VS Code again, so we can get access to the internal runtime. So you should see a link here. Code server can be accessed using this ngrok tunnel. Right? So just click on this. And then it'll open like VS Code. Right now, it's not pointed to the folder where Collab normally runs. So basically, if you just click open folder and navigate to content. And then you'll basically see the GitHub repo and all the artifacts downloaded and such. Again, these instructions are shared in the README of the repo, but I'm also open to taking any questions. Sorry, what's these shares? Okay, am I sharing the wrong slide? Oops, sorry. Let me stop sharing and sorry, share screen. Desktop two. Oh, apologies for that. Can you see my screen? This was the repo. The link to it was bit.ly PyTorch Workshop 2021. It's also shared in the Slack channel serving PyTorch models in production. And in the repo, there is the open in Collab button that you see that will show a starter notebook. Just click runtime run all. And once it's basically done, it will basically show you this link that you can open. And once you have this link open, you have a VS Code session, just click on open folder and navigate to /content. If maybe like people in like Zoom can just share like with an emoji, like if you are if you're having any issues or such, or if everything's good, maybe like a thumbs up. Okay, cool. I see one, so JS seems good. So again, while people are setting up, I will maybe just go over like one of the notebooks. Again, there are lots of notebooks that we will go over together, but let's just go over the first notebook. So the first notebook that we'll be reviewing is just kind of getting familiar with the libraries in the Hugging Face ecosystem, in the PyTorch ecosystem. So let's just wait for this notebook to open a bit. So it's taking some time. Let's click on it again. So you may see this thing, do you want to trust this notebook? It's fine to trust it, or again, you can see the rendered notebook on GitHub. So let me just duplicate these. And let me just duplicate the notebook so we can just compare the results. So since we are not using a GPU runtime, the numbers that you see here will basically be running on a very limited, will be running on a very limited machine. Like, so in fact, if we just look at this Collab environment, so this is only a 2-core machine with like 13 gigs. So this is a pretty not powerful machine. So just keep in mind some of the numbers that we see inside this notebook. And that's why it's different from the numbers in the committed repo. So let me just clear all the outputs in the notebook and let's just run this. So in this notebook, what we'll be going over is how to use the Hugging Face, like how to load a model that was trained with Hugging Face's library, both the model and tokenizer, how to use Hugging Face's dataset library, and how to see how to use how to run inference on this model. So Transformers is a library from Hugging Face that basically has where you can load a pre-trained model, where you can even train your own model. Torch is PyTorch from Facebook. TorchWiz is just a library to visualize the network. Datasets is a library from Hugging Face to perform like fast operations on datasets, to create datasets, to load your own datasets. So like the first thing that we're going to do is to load the model. So inside the model directory here, the still Bert cased, we have some model artifacts. We have the PyTorch artifact. We have some config files that Hugging Face uses to load. We have the tokenizer information that Hugging Face needs, and we have the actual vocab. So luckily, Hugging Face makes it simple to load all these things. Just call transformers.automodel for sequence classification, since our task is multi-class classification problem. So let's look at the model object. So the model that we trained is a distill Bert model. So we have about like 6 transformer blocks in this model, which does several things. and we have a classifier layer. So in this case, for this data set, we only have 31 classes, and the classes relate to like product types that you might see, like bed sheets, furniture, electronics, things like that. So one nice thing about Hugging Face is that inside the model object, you can basically give a map where you have the numeric IDs mapped to like a string label. So you don't need to necessarily have a separate artifact. Cool. So the next thing is let's load a tokenizer. Again, Hugging Face makes it very simple. So just call transformers.auto-tokenizer from pre-trained, and you basically give a directory where it is. In this case, since we have the tokenizer config in the same directory as the model, we just load it. And then, we see if the GPU is available or not. In this case, since we are basically using a CPU environment, this will be a CPU environment. So now let's just see, how to make inference on a simple query, right? So here's our query, like let's say cheap professional men shoes. Then we call the tokenizer.encode plus, where we basically give the query. We tell it that we want PyTorch tensors. We want to pad to the maximum length, which I believe is 512. And if this query was super long, we will truncate it too. So in this case, we have about like, what is this, 6 tokens, and the rest are zeros because there's no mapping. So these are the token IDs from the words. And we have the attention mask here, which just basically in our case just maps to the tokens that we have. So this is one way to call the model. You just call model and you just pass in the dictionary of both inputs. And here you get the logits from the model. And typical PyTorch or even TensorFlow, what you want to do is to apply softmax on this output, get the top predictions, convert to probability, and get the class labels. So here are the numeric labels. There's a nice helper function that PyTorch has, which basically you can map these things to the labels. So in this case, since it was like cheap professional men's shoes, we see like shoes was the product type that best matches with a high confidence. So that's basically how you use a PyTorch model, whether it's a Bert model or a regular BioSTM. And if you want a visual representation of what the model looks like, we can use this great library TorchViz. And we see we have the input IDs, the attentions, we see the weights, and this is a very big graph of the model of all the steps inside, which is very hard to navigate, but yeah. So if you're curious to look at specific layers and operations. But for our case, that's sufficient. So let's see, for the next part of the notebook, if you want like an interactive way to interact with the model, we just have like a simple IPython widget where you can enter the query and see the output of the model. If you just want to play it. Of course, you can just go in the above cell and change it. So, we covered how to load a trained model, how to load a trained tokenizer, and how to do prediction. But maybe in your use case, you might want to run it on a batch of input, right? So in our case here, we have a data set that we saved using Hugging Face's dataset library. We're just going to load it. So in our data set, as we showed, we had the brand, we have the item ID, item title. In this case, since this is a pure NLP problem, we only care about the item title, which is item name. And we have a train, test, and validation split. So this is just a usage of Hugging Face's tokenizer library, where we basically, for all these folds, the test, the training, and the validation, we're going to apply this function where we basically tokenize the text value inside there, and we pad it to the max length, and we truncate it. And since, again, this is running on a CPU, it might take some time. So this finished probably on the test fold, and we still have the train and validation. So we see like for about, it is an expensive model, right? It takes about 11 seconds to run a distilled Bert model, which is one of the smaller models we'll be covering today. So after we apply this operation, we should see like the input IDs and the attention mask. Again, this is a dictionary that we fed on a single prediction. So here we have, you can think of this as a pandas data frame that basically have these fields. So since we're not running on a GPU, let's just take the first 20 outputs of this. And we can then basically, so now there's several ways we can do a batch prediction on this full data set, right? So if you can use the Hugging Face ecosystem, there's the transformers.trainer object, which is the same object that you might have used for training. And you can just basically call trainer.predict and you pass like the Hugging Face data set, and it will automatically use all the GPUs in a very efficient manner. And the Hugging Face dataset library has all the popular metrics that you might have used, accuracy, F1, precision. Basically, you can load this object, and then you can give it your actual predictions and the reference predictions, and it will compute the accuracy. In this case, since we don't have a GPU, so we only took the top 20, so the accuracy number is not that meaningful. So, that's basically how you might call the predictions on a batch. If you want to like feed, you can also use, like the Dunder method and basically pass like the input IDs and attention mask. But what you need to do is you need to be careful that the tensors, once it's loaded, and the model also fits all in like memory. So that's basically it. I think this is all I wanted to cover for this notebook. Hopefully you guys got a flavor of how to load a model and how to run inference on it. The other notebook we wanted to cover today, and we're not going to run this because it does take some time, is to look at the timing information for the different BERT models and BERT architectures. So as Avi mentioned, like there's BERT base, BERT large, and then there's also the distilled version of these models. And we'll cover what distillation is a bit later. So the numbers again here are running on, so I'm not going to run this notebook, but this notebook was run on a 16-core machine with a NVIDIA T4 GPU. So here again, we're using the great Hugging Face transformers library to load a pre-trained BERT large uncased model. And what I want to highlight is the time it takes. So like on a CPU, this model takes about 847 milliseconds on a single input batch size of 1. On a GPU, it goes to 300 milliseconds. So it's still not within our SLA, right? So it's pretty high. So now if you take like a smaller model, which I think if BERT base had 12 attention sets, this is 6. So BERT base, we see that the CPU inference took 251 milliseconds. And if you run it on a T4 GPU, it takes about 45 milliseconds. So we see some improvement, and like we're getting closer for BERT base, but it's still a little bit on the large end. Now, if we use a distilled BERT model, we see that we go from 125 milliseconds on the CPU and 26 milliseconds on the GPU, and this is without any optimizations. So now we're getting a little bit closer to kind of the SLA that we need to meet. So, these are the two notebooks. Hopefully you guys were able to have everything set up and follow along with the notebook. And, if you weren't able to follow, that's fine. We have 2 other notebooks that that you don't need to have completed running this notebook. So let me go back to the slides. Are there any questions before I go to next? So, okay, I think hopefully everyone is good. Hopefully everyone is set up. If I could just see like maybe like an emoji just to see if like everyone was able to follow along before we go to the next section. Okay, I see one. Hopefully everything is good. Again, feel free to post on the Zoom chat if any issues. So let me just go to present. Hopefully you can see my screen. So, okay, So we covered two notebooks. We saw, how expensive some of these BERT models can be, and we saw like the distilled BERT model. The SLA on GPU is kind of probably within our range. So now let's look into like some model optimization techniques that we could do to further improve the performance. So the first technique that we're going to look at is quantization. So, when we trained our model, we used 32-bit precision. But, for inference, do you really need such a high precision? Most of the time, we could probably convey the same information with probably a lower precision, 16 bits, and maybe 8 bits, 8-bit ints. And you may see a drop in accuracy, but it may still be useful for your use case, especially considering the memory and computation speed up that you might see. So on most hardwares, int8 computations is much faster, probably like on a factor of 2x to 4x compared to floating point 32-bit precision. And most of the time, depending on your problem and data set, like the drop in accuracy from quantization may not be much. So on the right-hand side, you see an image. So basically, if you're using 32-bit precision, you might have like a large range where you might have like a max and min, and you can see values, continuous values in that range. And, maybe all your values that you actually see for your model, like for the weights or activations, might not be within that range. So what you can do is, you can quantize it. And, with things like rounding, clipping, and finding the right mapping function for your layer, you can probably create like the graph that looks like below. And it may work for your use case. It may capture enough knowledge that might be needed. So in PyTorch, we have 3 different types of quantization. All the quantizations that we're going to cover are going to quantize the weights, but there's some other differences where they differ. So the first one we're going to cover is dynamic quantization. So as I mentioned, all the weights are quantized in whichever strategy that we're going to cover. But where dynamic quantization differs is it doesn't quantize the activations. So the activations are quantized dynamically on the fly. So you feed your tensor, you multiply by the weights, you get your activations. The activations are converted to ints, then it's multiplied with the next operation, and then it's converted back into floats. So you don't really see any memory improvement, but you do see a speed up because you're doing the large matrix multiplications in int8 math. Yep. So let's see how to use dynamic quantization. Now, PyTorch makes it very simple. So here, if you have your 32-bit float model, you can call torch.quantization quantize dynamic, pass in your model, you pass it a list of layers that you want to pass to quantize, and you pass what type you wanted, either 16-bit or int8. So that was technique 1, which is the most simple and which is also the recommended technique for like transformer models like Bert. The second technique is static quantization. So static quantization, here the weights and activations are both quantized. So in order for the activations to be quantized, there needs to be a calibration data that needs to be provided. And one of the beautiful things about this is, since the activations are also quantized, like you don't have this like constant conversion from floats to ints. So inference is much faster in this mode. The other thing to think about is, if you're going to quantize the model, you might as well look into something called quantization aware training. Basically, what you can do is like, when you define the training loss for your model, you can tell it to consider what you can also tell it to consider the quantization error loss. So basically, when the model is being trained, it will find the best architecture, best weights that also minimizes the quantization error. And this method leads to best accuracy. So let's look into how these 3 different techniques that we just covered, how they, like what are the improvements they may bring. So the first result that we have, first row is for Bert. we see that for, if you use 32-bit precision, we get about a 90% accuracy. But if we use int8 precision, we drop by 0.05%. But if you look at the speed up, we get a 1.8x speed up. Again, this is not on a GPU, this is on a CPU. So we went all the way from 581 milliseconds to 313 milliseconds, which is a pretty great speed up. If you look at the CV model resting at 50, we see a drop of 1% in accuracy using static quantization. But we do see like a 2x speed up. So for a 1% drop in accuracy, a 2x speed up, especially in production, is a great use case. Now for the final model, MobileNet V2, we see, so this model, it does suffer a little bit from quantization. So when we use quantization of our training, we only see a 0.3% drop in accuracy. But the last row, we're running on a Samsung S9, so which is a phone. So we're seeing a 5.7x% speed up. So obviously on phones, they don't have the compute power of like your server or desktop. So floating point operations are even slower. So that's why you see such a big improvement. So, we covered quantization. The next optimization technique that we're going to cover is distillation. So for distillation, we have like large models like Bert. And, this model is great. It has a very large knowledge capacity than, like your simple models like BioSTM. But, maybe for your problem, you don't really need all that learning capacity, right? So, won't it be great if, your smaller optimal model, if you can tell it to maybe mimic what the larger model is learning for your problem. So basically what you're going to do is, you're going to take your BERT model, make it act as a teacher model, and then you're going to take your smaller, let's say BioSTM model, you're going to tell it to be a student. You're going to tell it to basically try to mimic the loss and prediction that the teacher network is giving for your data set. And the goal is like, because your student network is maybe small, it might not be able to explore the large hyperparameter space. But by having the teacher network already learned and doing well on the problem, you're helping the student network kind of reach a convergence or reach a better accuracy. So let's see, what is the effect of distillation in practice. So if you take a look at the second row, so here we have a BERT-based model, which has a 93% on the Stanford sentiment analysis data set. And then if you look at the last row, which is the BioSTM. So the BioSTM model by default only has 86% accuracy. So if we do distillation from what we talked about before, we go all the way to 90.7%, which is a great improvement from. And the great thing is also you're using the BioSTM, right, which is pretty inference efficient, but now you're able to increase its accuracy. So we covered quantization, we covered distillation. Let's look into the last optimization that we'll be covering today. So the last thing is eager mode and script mode. So one of the many reasons why PyTorch became very popular is the fact that it was very interactive. It was easy to prototype and debug. What powers this is because PyTorch by default runs in eager execution mode. So eager execution mode allows us to get immediate feedback from our Python interpreter. You have your layers, you can pass in your tensor, and you get feedback from that without like creating the graph. You can use any of the libraries in the Python ecosystem, but this reliance on the Python process makes it a little bit slow for inference in production. So so what you can do is, once you're done training, you can explore using script mode. So in script mode, what you basically do is you take your model that was trained on eager execution mode, and then you create an optimized graph from it. And the beauty of this mode is, you're not tied to the Python process anymore. You only need to rely on a C++ runtime. So if there are other languages that your production models are being served in, as long as they have their language bindings to the C++ runtime for libtorch, then you can basically use PyTorch in your environment. The other thing to note is when you use script mode, you're technically not using PyTorch, you're using TorchScript. So TorchScript is an optimized representation of a PyTorch model. So it doesn't really support all the operations that you might be able to use in regular PyTorch. And it also doesn't really support Python data structures. But the speed up from script mode is significant, so you might want to consider using it. So let's see how we can convert the model from eager execution to script mode. And in this case, we'll be using PyTorch's just-in-time compilation. So PyTorch has the just-in-time compiler, and it supports two modes, tracing mode and script mode. So the tracing mode supports, it's the most simplest to use, as long as you're not using Python data structures inside your forward method. It's very easy to use. You just pass it a sample input, and the just-in-time compiler will look at the execution graph and create the optimal execution graph for that. The other thing is, other mode is script mode. So if you do need to use a custom control flow, or if you need to use Python data structures, you're limited to script mode. You do get some of the benefits of some speed up, but it's not significant. So let's take a look at it in practice. So here is a simple PyTorch model. If you notice in the forward loop, we have a if-else block. So because there's this Python conditional, we can't use the trace mode that we use. So we had to use script mode. So yep, this is again very simple for PyTorch to run it, and you just call model.save, and now you have your just-in-time compiled model running in script mode. So let's see how much improvement we got from this approach. So we have two columns here, the CPU inference time and the GPU inference time. So just that one line, doing the torch.jit.trace or torch, so we went from 1.3 seconds all the way down to 768 milliseconds, so 42% improvement just from that one small change. On the GPU, we saw a slightly smaller improvement, but it's still significant, I would say. So we looked into three techniques, right? We looked into quantization, we looked into distillation, and we looked into converting into trace mode. All these approaches that we talked about is we applied it to our model in production. So now we're about to go to the next lab where we basically just kind of work through some of these approaches that we talked about. So I'm open to taking any questions that we have on this. Okay, so I see one question from Edwin. Is the training time the same or more with quantization aware training as it would be without any quantization? So from what we saw, the time was not really significant because it's just like an additional metric that it is taking. Yep, cool. Are there any other questions? Cool. Cool. Okay, so let's get into workshop 2. So again, here's the link, the bit.ly link to the repos. Hopefully you all have it. And we just did this first step to open the Collab environment. Hopefully you're all set there. And once you have your VS Code environment, we'll see this notebook tree optimizing model. So again, I'm just going to duplicate this in case we want to look at the previous run. So see, let me close this and try opening this again. let me click trust this notebook. So in this notebook, what we're going to do is, again, the steps that we did before about, loading the artifact, loading the model. What we're going to do is quantize the model and then use TorchScript to convert the model to script mode. So let me clear all the cells. And yep, so I'm just going to run over some of the initial cells because they're just basically loading the model and artifact, which we covered last time. Okay, so the heart of the notebook will be this section like optimizing, quantizing the model. And as we discussed, PyTorch supports three modes. In this case, dynamic quantization is sufficient for our case. So I'm just going to wait for it to run a little bit. Maybe while it waits, I'll just go over some of the cells. So as we saw in the slides, we can just call torch.quantization.quantize dynamic. You just pass in your model and you pass which layers. For this case, for the Bert model, I think it's sufficient for the linear layer. It'll give us enough improvement for our case. And let's see, how are we doing with the earlier steps of running? Okay, I see we loaded here. Okay, great. So I'm just going to put the model to the CPU, although there's only the CPU in this runtime since we're not using the GPU. So let's apply quantization in this model. So let's see how much space we gained from doing this quantization. So if you just look at the file size, we went from 267 to 138 megabytes. You might expect a little bit, larger thing since we're going all the way from 32-bit to 8-bit, but PyTorch uses some other data structures to kind of keep track of some information. So that's why you don't see quite the storage space, but you'll definitely see the inference time improvement. So let's try to run a benchmark on the original model, the 32-bit model, and the quantized model. So since I don't have a GPU, like just in the evaluation loop, we just return if a GPU is used. So, but if you are able to get a GPU, feel free to run this in that environment. So let's see how much improvement we got from doing this quantization. So here we are, again, this is the 32-bit model, and this is the, oops, sorry, I should have run this cell. So, okay, so this is the 32-bit model running for a couple of iterations, and then this is the quantized model. So let me just run this. So we saw like from a single iteration, and maybe it might need some warm-up, it took some time. So here, let's see, it's saying it took 878 milliseconds. And again, this is not a very powerful machine, but still it is a little bit high, right? So let's see how much time we got from just doing this small quantization improvement. So I realized I put the timing a little bit different. Maybe while this is running, okay, so 618 milliseconds, right? Unfortunately, right now, like PyTorch doesn't support dynamic quantization with CUDA kernels. So we don't have this measurement. But if you look at the improvement that we got, again, this number here is on a slightly different and more powerful machine. But if you look on that benchmark, we got 116 milliseconds for the 32-bit model. When we did quantization, we went to 83. And on a GPU, we were getting 17 in this run. And one thing to keep in mind is like, it depends also like on how many threads, like the underlying C++ library sees that it can use. So here, like, it looks like it's only seeing like one thread with a concurrency of 2. And on the other environment, that we ran, we have 16 cores. So that's why like the numbers that you saw here are maybe not as significant as you saw on the slides where it's running on a clearly, on a purely single-threaded machine. So we covered quantization. Now let's look at the other mode, which is basically tracing the model to make it run on an optimized executed graph. So one thing you need to do is, if you're using Hugging Face, is you need to pass this flag TorchScript equals true when you load the model. And this basically like kind of decouples some of the layers that kind of how Hugging Face has the model architected, which kind of TorchScript doesn't really like. You can find details like on the docs here, but for now we can just pass this flag, and Hugging Face kind of decouples the embedding and encoded layer. So we have the model and tokenizer. Again, this is not really running in trace mode. This is just like some internal decoupling that Hugging Face is doing. So to actually use it, we just call torch.jit.trace. You pass in the model, and you pass in a dummy input. So Hugging Face can, PyTorch can kind of look at a model and how the graph is executed to create the optimal graph. Yep, so it came. So again, this is just running it. So just maybe in the interest of time, let me just go to the timing information. Or let's just see. So when we ran it on the slightly powerful environment, we saw that we were getting 130 milliseconds for the original model with 32-bit precision on CPU. After tracing it, it became 124. But once we do both quantization and tracing, it became 89 milliseconds. And you can run the other cells in the notebook, but we already have all the artifacts saved. So I'm just going to go over the notebook towards the end. So one thing you need to do, and it's important for the model serving, is you need to create a map of your string labels to classes. So there's this data structure which Hugging Face already has as part of the model. And this is one of the things with when you trace the model, TorchScript doesn't really support some of these Python data structures. So in order to do the mapping from your numeric labels to string labels, you need to keep track of the classes, the human-friendly names by yourself. So we'll just save it in a JSON file. Some other thing that might be useful for later use cases, you might want to have some artifacts that are packaged as part of your model, right? So maybe you want to keep track of, hey, do I need to lowercase? Do I need to tell the tokenizer to lowercase the model? How many labels did I have? Is the artifact that I'm bundling as part of my deployment, was it traced, or is it just a regular 32-bit precision? And how much do I want to get a top 5, top 10? So this is a deployment option that we will cover later, but basically the idea is you can package whatever artifacts that you need as part of your deployment using TorchServe that we'll cover soon. So that's basically what I wanted to cover for this notebook. And the basic idea was to show that you can get pretty good improvements with doing some of these small optimizations. And again, they may not seem significant, but when you are dealing with millions of requests, all these small things do matter. So this is what we had for section 2. Now my co-presenter, Avi, is going to show you how to take all the optimized model and how to actually serve it with PyTorch's TorchServe. So I'm going to stop sharing.
Yeah, thanks a lot, Nidhin. Okay, so let's dive into how to deploy the model and the steps required. So we had a couple of options to deploy the PyTorch models. Pure Flask or Fast API was a way to go. Then the other machine learning frameworks have their inference servers as well. So TensorFlow has TensorFlow serving. NVIDIA has come up with NVIDIA Triton. And then we have TorchServe. We went the TorchServe way, and I'll run into a couple of benefits of using TorchServe. So to start with, TorchServe is highly optimized. It has configurable support for CUDA and GPU environments. And since most of the need that arose for us was to run in a GPU environment, it made sense for us to go the TorchServe way. TorchServe has multi-model serving as well. So you can host multiple versions of the same model at the same time on the same server. So that's particularly useful if your team wants to perform some A/B testing. You can run traffic, you can split traffic between both the versions of the model at the same time. There's some tremendously good support for server-side batching in PyTorch, in TorchServe. I'll run through a slide in a bit where I will show you the configurations. It abstracts most of the effort required by the developer out. So it requires minimal to no effort on the developer's part to write logic for this batching piece. You just need to provide the batching size and the batch delay parameters in the configuration files, and then TorchServe takes care of the rest. And it has some really good support for pre and post processing as well. So TorchServe has custom hooks and custom handlers, which are required to be overridden, and any special logic for pre and post processing can be added in those hooks. And then again, TorchServe picks it up on the fly. So how to model how to package a model. A model file is packaged. A model is packaged into a MAR file using a Torch model archiver, which is a utility given to us by the PyTorch team. It bundles up all the dependencies, all configurations, all the files required to run the model at runtime in a single artifact, and then this artifact is then loaded into the Torch server. So you can see the command required to bundle up the model files. Very straightforward. We'll be running through a small demo during the hands-on in a bit. So I'll touch briefly upon how we're making use of this handler at Walmart. So since multiple teams need to host their models on TorchServe and then further take advantage of the CUDA capabilities, what we have done is we have made a custom handler which extends the base handler that PyTorch provides. Now it acts as a top layer on top of the base handler. So any common initialization, any common pre-processing, error handling, metric collection, any of these steps that are required, that are common across a lot of model hosting teams, these are abstracted out of the developers, and we take care of this. So again, the point is to minimize the effort required to host models, and then to hasten up the process. So it gets very easy for developers to host models on the fly. Any model-specific logic that the developer needs to add will then be added in these custom hooks. These are the hooks I was talking about. So pre-process, inference, and post-process. Any pre-processing logic, any tokenization gets in here. Inference logic, your models are being called inside the inference hooks, and the post-process as is self-explanatory. So it's a resilient wrapper that can be extended and used by multiple teams across the company without the need for each team to set up a similar handler for their use cases. So PyTorch also has support for these handlers. So the use cases are image classifying, image segmentation, object detector, text classifier. It's again fairly straightforward. Just provide the model file and then a JSON file, and PyTorch takes care of it. So this is what the configuration file looks like for torch serving. Just provide the inference management and the metrics addresses. So here we have configured the ports to be 80, 80, 8081, and 8082, which is, I think, what usually is used. Number of you can configure the thread pool size. You can configure the batching configurations here, which is what I was talking about earlier on. So batch size 20, batch delay. So very straightforward. Again, no code changes required. and TorchServe fix it up. So there's a management address, there's an inference address, and there's a metrics address. For the inference address, that's where you run your inference. For the management address, TorchServe provides an API for us to scale out torch workers on the back end for a CPU-based environment. The number of cores in the CPU is what is set as the number of torch workers on the back end. For a GPU-based environment, this can be configured. So here's an example for the management API. Just get the details with these APIs. So we'll jump into another hands-on session. Here we will talk about how to package the model as a MAR and then run some live inferencing. So again, going back to the notebook that Nidhin was sharing, if you go to the fourth notebook, I'll just show you what the model files look like, what the working directory is. So here you have all your model store. The model is hosted inside the model store. The tokenizer files, vocab files, they're all part of the MAR bundle. Now the Torch model archiver, just run a help and you'll be able to see all the flags that are provided along with the CLI. So let's run this. So it's going to load the handler. That takes a bit of time. Let's run this. Okay, so we will not be able to see the logs here right now, but we've started the torch server now. Let's tail the logs. And okay, so these are all the log files that are available to us at runtime. So the metrics go inside the model metrics, access logs, and the access logs. TS stands for TorchServe. All the TorchServe metrics go in here. Tailed again. Okay, there we go. The work has started. So let's see the configuration file, what it looks like. So all the models that are loaded inside the model store will be loaded. You can selectively whitelist or blacklist some models as well. Again, inference address running at 9080, management 81, and metrics at 82. Let's see. So this API provides to us, it's a management API call, provides to us all the models that are loaded currently on the Torch server. So right now we have the product type classifier as the only model that's running. If we append the name of the model to this API, we should be able to see the number of workers that are loaded. So right now you can see there are 2 Torch workers running, batching configurations. Everything is here, all read from picked up from the configuration file. Let's run a sample prediction on the inference API. There we go. So we've used verbal T as a query, and then we see that it's classified the query into product types along with their confidence scores. That's about it. You should be able to run the live inference on the server if you have the notebook running. That brings us back to the presentation. The lessons that we learned. So we used a distilled version of the Bert-based model along with quantizations and other optimizations And this is, I'm talking in context of the search team at Walmart. And we served this on a CPU, and our latencies were below 40 milliseconds, again, below our SLA requirements. But when we ran this on a GPU-based environment, the GPU here used was an NVIDIA T4 Tesla GPU. At peak traffic, we were seeing under 10 milliseconds of latencies, along with a throughput of about 1,200 to 1,500 requests per second. Again, well below our SLA. We're targeting our peak traffic, daily usage, and holiday usage as well. So here's a chart. This is where we are showing our inference latencies. You can see everything is below, in fact, 7 milliseconds, not even 10 or 9. Okay, I'll open the floor for any Q&A now. Please check out Walmart Global Tech for openings for software engineers, machine learning engineers, or data scientists. We're always hiring. Yeah. By the way, I saw a question in the comments that said whether quantization affects the training time. Yes, quantization does bring up the training time, but then you're improving drastically on the inference times as well. Thanks a lot for joining the call, and have a nice Friday. Have a nice weekend ahead.